And next up is James Sloan. Is that the correct pronunciation of your name?
Yes.
Good. And you have been trying to become a lunar settler for 60 years. Is that correct?
That's correct. Okay.
Yeah. I've been an Air Force officer, getting a bit up, I guess, and have a master's degree in international relations. And the last 10 years, you have been working full time on settling.
Hmm.
So, with no further ado, please, the floor is yours to talk about the basics of space radiation and the
Okay.
challenges it presents.
Yeah. Okay. And so, in terms of units of radiation, we have rad and rem. These are older terms that have since been replaced by Gray and Sievert. And this was to honor Dr. Gray and Dr. Sievert, who were pioneers in the study of radiation. Now, a rad is a unit of energy that is absorbed by the body. REM is a measure of the damage that occurs due to this energy delivered. One gray is equal to 100 rads, one sievert is equal to 100 rems. Now, because of these numbers, you commonly see the use of prefixes on gray and sievert. Centi for 1/100th of say a gray, or milli for 1/100th of a sievert. Either of those prefixes would apply. So we have 10 millisieverts would be equal to 1 rem, which would be equal to 1 centisievert. Now, there are three parts we really need to concern ourselves with. The first is the proton, the next is the iron nuclei, and the third is the neutron. So 1 gray of energy E delivered by protons is equal to 1 sievert. And so you often see grays and sieverts used interchangeably at this point. But when we look at iron nuclei, 1 gray of energy delivered by an iron nuclei is going to be equal to 12 sieverts of damage. And so it's not only a matter of the energy that is delivered, but the method that the energy is delivered by. Additionally, iron nuclei, or rather all the atoms, the rate at which they discharge their energy is roughly equal to the square of their atomic number. So the iron nuclei releases its energy at a rate 676 times faster than the proton does. And in the case of the neutron, we also see that there is 10 sieverts worth of damage with 1 gray of energy absorbed. Now, there are two radiations that we need to consider. The first is solar proton events, and the second is galactic cosmic ray radiation. So, with solar proton events, they're characterized by very large numbers of particles, but they also have low kinetic energy particles. They typically are on the lower end of the energy scale. They are also sporadic, and so they're analogous to a weather event. So you might see one SPE occur in a year, and it would be of a 10 to 15 hour duration. Because of the enormous number of particles, they deliver a considerable amount of damage to a human being, and they are considered to be life threatening. Now, the galactic cosmic rays, they are a relatively low number of particles, but they have high kinetic energy. They are essentially continuous, and they represent a health threat rather than being life threatening. So in galactic cosmic rays, we think in terms of the risk of developing cancer from the exposure to, this radiation. With the difference between low kinetic energy particles and high kinetic energy particles, when we are putting up a physical shield, we're trying to render the particle harmless by absorbing its kinetic energy. So the lower the kinetic energy, the less material shielding we need to block those particles.
James, if you press the F5 button, you should get full screen so we see better.
Okay.
On the computer, F5.
Okay.
Okay, it was worth a try. Proceed.
I don't know. Very very method has, of course, so seafood often in the case 20 grams works out kilograms per square meter uh, uh, to about 1,500 square meter. So this provides us with a protection of about a factor of 100, reducing the incoming radiation by a number of 100. So in the case of galactic cosmic rays, we need, though, on the order of about 400 grams per square centimeter to reduce the incoming galactic cosmic rays by a factor of 10. So that shows the key difference between SPEEs and galactic cosmic rays. We need much, much more shielding for galactic cosmic rays. Now, this is a chart of a solar proton event. They are normally named by their month and year. Damage that was received by this event, with the lower figure here being the amount of shielding mass, reducing the damage. And these two events, this event here is actually the October 1989 event, and this shows how making a choice in how to essentially diagram the spectrum of the particle radiation can affect the estimates of damage. So one is based on the Weibull function, while the other is based on an exponential spread of the particles. Radiation from galactic cosmic rays, and so at the 20 per square centimeter mark, we see a marked reduction, but then the curve flattens out, and I'll go over why that curve flattens out. Okay, we have cradle. It's often thought as a child's toy. It shows conservation of momentum. And so when a cosmic ray proton enters into the shielding mass and strikes the nucleus of an atom of the shielding mass, basically all of the original cosmic ray particles are captured very early in the shielding mass but the energy of those particles propagates through the shielding mass. And so with the nucleus, when the cosmic ray proton hits the nucleus, it delivers its energy out, and another proton will go out at almost the same speed that the cosmic ray proton came in. There's some loss, and we want that because we're trying to reduce the energy of the particle to a point where it is essentially harmless. Now, the problem is with a nuclei is not composed solely of protons, it's composed of protons and neutrons cause 10 times more damage than the proton does. So, what we saw in the galactic cosmic ray chart is that the first damage that appears with cosmic rays stems from the iron nuclei. Now, the iron nuclei, because it is so energetic, it releases energy so quickly, and because of the immense damage that it does, that even though the iron nuclei is only 1% of the incoming galactic cosmic rays, it causes the bulk of the damage. But then, as its energy is absorbed by the physical shield, the galactic cosmic ray protons are now transmitting their energy into the nuclei and expelling neutrons. So the first metric ton of shielding material is really showing the transition between galactic cosmic rays, the iron nuclei, and the transition to neutron radiation. So following the first 100 grams per square centimeter, we're now seeing essentially neutron radiation. To attenuate the neutron radiation by a factor of 10, we need 300 grams of shielding material. And so for every 300 grams of shielding material, we see a further reduction of factor of 10. So for a space settlement, you'd want 600 grams of shielding material. You have 100 grams for the transition material, for a total of 700 grams to reduce the incoming radiation to 1/100th. And then we commonly see 10 metric tons or 1,000 grams per square centimeter, which is basically the amount of shielding material that we have with our Earth's atmosphere. So those are essentially the two numbers you see, either 700 or 1,000 grams for space settlement shielding. Okay, so NASA has established some rather conservative radiation limits by age and sex. Now, in this case, solar proton event radiation would not be considered. It would be assumed that any astronauts would proceed to a storm shelter during a solar proton event. And so this only refers to galactic cosmic ray radiation. And from this, the limits that are set for a 30-year-old male astronaut, and the limits are set by age and sex. The male maximum dose would be 62 centisieverts, and this would be expected to be received in a spacesuit or an unshielded habitat over the course of 284 days. So that would be the entire time that an astronaut could remain on the moon. And so this increases with age. And thing to understand is that if we're dealing with a deeply buried base, then this would represent suit time. And since a comet, well, I'll get into that in a little bit. is a less conservative uh, uh, that I put together. Basically, it still uses the same limits that NASA uses for the total dose, but it's assuming a much less radiation and level per day. The previous slide with NASA assumes a lot of uncertainty, and so they compensate that by assuming a much higher radiation dose per day. Okay, so what would we likely see with Artemis? In the case of galactic, I keep getting the thing. My internet is unstable. Okay, Artemis will likely employ, I think, 20 grams per square centimeter shielding over the entire base. Uh, Now, the reason for this is that as the iron nuclei is absorbed, uh, we hit this flat curve that has that in which damage to the individual is unchanged. So we see a marked reduction in damage from 0 to 20 grams of shielding, but past 20 grams of shielding, we now have to go to more like 100 grams of shielding for galactic cosmic rays, and then an additional 300 to reduce it by a factor of 10. So 20 grams gives us about a 20% reduction in the incoming galactic cosmic radiation. So now, to deal with the limited time that an astronaut would have on the moon, I would expect 4 teams of lunar astronauts staying 90 days per year on the moon, and then NASA rotating their astronauts so that a 30-year-old male astronaut would be able to serve 3 tours on the moon before they would reach their radiation limit. Now, 20 grams uh, mass is equal to 2.5 centimeters of steel, say equal to 8 centimeters of glass, or 13 centimeters of regolith. Artemis will likely use a storm shelter to protect the astronauts from solar proton events. This is, and I'm estimating that 100 grams of shielding for the storm shelter. If we go beyond 100 grams, then we start seeing also a reduction in galactic cosmic rays, in which case, rather than having a simple storm shelter, I would expect that NASA to make use of that area as, say, sleeping quarters to further help reduce the galactic cosmic ray effects. Now, in deep shelters, again, we have 1 metric ton is needed to transfer the energy of the incoming galactic cosmic rays to neutrons, and then 9 metric tons to reduce it to an Earth normal radiation environment. Now, I showed the amount of time that we could expect suit time with a deep buried shelter. The individuals would be exposed to galactic cosmic rays only when they go out on the surface, and the probable mission time for surface work would be 4 hours on the surface. So if they went out 4 hours a day, 6 days a week, then there's a 7-to-1 ratio. So if a astronaut can remain in suit time for 1 year, then that would be spread over 7 years for a career life. And if we cut the time from 6 days a week to 3 days a week, then that would be spread over 14 years of career life.
And thanks a lot, James. I think you made it just in time, despite the troubles at the beginning. Yeah, that's the
Yeah.
that's the timer. So thanks a
That's it.
lot. And unfortunately, we don't have time for questions online. But if anybody has question, please write and type them in chat, and hopefully James can answer them offline or in the chat.